Okay, so hello everyone again. So today we'll be starting with our discussion, continue with chapter 10. It's all about radical reactions. Now, so in the previous meeting, we talked about the uh, allylic radicals being stabilized. Okay, last meeting again, we discussed about the allylic radicals now, which we can see that it is being stabilized by electron delocalization. And in fact, we were able to see a resonance hybrid in such a way that there is an important reaction that we can see with allylic radicals. In this case, we can have the bromination reaction at the allylic position from that of the double bond, and then you can have your, for example, bromination reaction. And it is different from what we have learned with alkene, that whenever you have a bromine, for instance, or a halogen, any halogen on your alkene, that it will be added on your alkene here. In the bromination reaction, when you have an allylic position and you have your source, for example, of your bromine, the bromine will be substituted, not or will be not be added onto the double bond, but it will be substituted on the allylic position. So the hydrogen here is being substituted with bromine, and one of the source of our bromine is the NBS, or we have the N-bromosuccinamide. What is that? This is the we have learned this one in the last meeting, and this will be our source for bromine. So this is our N-bromosuccinamide. Okay, and whenever you have this reagent in the presence of a peroxide, our reagent, you will have, whenever you have a peroxide, you always have to remember that it is always a radical kind of reaction. And in the radical kind of reaction, of course, you always have to produce radical. Once you have your peroxide, you always have to produce your radical that will initiate the reaction, and then you will have the substitution reaction on the allylic position. So again, we have discussed that last time on the mechanism of the reaction of the radical reactions. Of course, once you have your radical, you always do substitution reactions with your halogen, and they've learned on the stability of the allylic radical last time. It is more stable even for a 3-degree radical, or 2-degree and a 1-degree radical, and even more with a vinyl radical. And this trend is the same trend that we have learned with carbocation ions. Aside from the allylic radicals, we also have an important radical that is also being stabilized by electron delocalization, and that position is what we call as in the benzylic position. So what is that benzylic position? You have your benzene ring, and you have this carbon benzylic position. Your carbon and hydrogen on the benzylic position, and if you have your radical on that position, we actually have a very stable radical now, which is stabilized by its pi electrodilocalization. So for instance, you have this benzylic radical in here. Now we can always have this contributing resonance structure stabilized by pi electron delocalization. So when we reach on the chapters, aromatic chapters, now we will discuss more on the stabilization brought by pi electron delocalization sa atong benzene ring. And so here we have shown before in the last meeting, the discussion on how the radical can be stabilized by pi electron delocalization. So for instance, here you have your electron here, an add electron or your radical here, it can be stabilized by stabilization by the adjacent pi bands. No? So you have your pi bands here overlap sideways to this other carbon-carbon here. You can actually stabilize this one. This one also, this pi radical or this, not pi radical, this radical here on the benzylic position is adjacent to this pi band here. So they are parallel to each other. They can overlap and can form a bond here. And when they do the localization, the electron, the add electron will go here, by homolytic band cleavage to this pi band. You can form your pi band here, and you have your dot here. And another resonance position, you have your Gani share. You can also break this pi band here by homolytic band cleavage. You can form a bond here. So your radical will then be situated here, and there's actually 1 to 3 contributing structures not to form your resonance hybrid. Because of that benzylic position of your radical actually is very stable, and it's the same stabilization by both by the pi electron delocalization as with the allylic position for your radicals. Okay, and for that can actually have also a reaction on the benzylic position with a substitution here for your hydrogen, forming a radical here, benzylic radical, to be substituted with the halogen here. No, so you don't react with the double bonds sa imuhang aromatic ring. Okay. And here you can see that because of this very stable benzylic radicals compared to a 1-degree radical, the reaction with this substitution reaction with halogen actually is very fast. So for example, you have this reagent or reactant, and of course you have your halogen radical, your source to produce your radical. So between a benzylic radical and a 1-degree radical, the benzylic radical is actually very stable, that it will proceed the reaction to proceed. The product is very fast. The reaction to proceed this product is very fast. Okay, so whenever we have to choose which reaction will be more favored, is it in the 1-degree radical or a benzylic radical? The reaction is much more favored whenever you have a benzylic radical, or whenever you have a hydrogen to be substituted with a halogen at the benzylic position rather than at the 1-degree position. Okay, so you take note of allylic position and benzylic position whenever we do substitution reactions, particularly when you have your reagents having your peroxides. Because later on, there will be a lot of reagents that will be mixed for every functional groups that you will meet. There are so many reactions. You always have to remember that whenever you have one of the reagents as peroxide and NBS and the likes, it will always proceed by the mechanism of radical reactions. And then you will have to think of the mechanism behind. We've learned that in the previous chapter. If you want, you can review on that when you have time. Can go back to the video because it's been like 1 week now that naka-meet or more. Okay, so what is this? So for a problem, this question: when propylene benzene radical reacts with chlorine in the presence of urea, the major product is 1-chlorophenylpropane, of both 2-chloro-1-phenylpropane and 3-chloro-1-phenylpropane are minor products. Yeah, so this one is you have your phenylchloropropane, and can have this application to your benzylic radical or is the 1-degree radical. And here you have your chlorinated alkyl halides, or alkyl halides rather, in here. So the reaction will have here, right, the structure of the radical leading to each product account for the fact that you have here 1-chloro and 1-phenylpropane. Of course, the first steps you always have to write on the structure of this. So 1-chlorophenylpropane, you have your phenyl, and you have your propane. Phenyl group like this one. Okay, and propane. So you have to write the propane, CH3. So here is show how phenylacetylene, you have phenyl acetylene 1, 2. C6H5 phenyl is C6H5, this part here. You can go back to the naming, and then C triple bond C, that's your acetylene. So phenyl is whenever you have this ring here. Okay. So, and then show how phenylacetylene could be synthesized from ethyl benzene. So this is your ethyl 1, 2 benzene, and this is your phenylacetylene. Okay, and ethyl benzene or phenylethyl. Begin by writing retrosynthetic synthesis. So, okay, show na siya diri. So, this is our target product, and we'll start with this one. So, we'll be asked, how do we proceed to this if our starting material is this? Okay, so you can go for the retrosynthetic pathway, like for instance here, how do you obtain from this triple bond, no? And you can think before this, thinking this one, that this can be prepared from this reagent. Remember the hydrohalogenation reaction, no? You can have the alkyl halide to be eliminated. You have the 1,2 elimination reactions. You can eliminate this to actually produce this one. So first you have your alkene, and then second elimination you have your alkynes. Okay, and then you can think, how do you prepare this one? Okay, how do you halogenate this one? Then you can think of this from your starting material, like this part here is simply just an alkane part. And from here, you can actually do halogenation reaction to produce this one. Or alternately, you can have your kani can be prepared this way or this way. Okay, the first one to elimination reaction is your katong to produce your alkene. Then second one is this one. No, you have your Br can either be on this side or this side. You have 1,2 elimination reaction kaduha. So you have two moles. The first one is the first hydrogen and bromine to be eliminated to form your alkene. The second one is also your hydrogen bromine to be eliminated to produce this one. Or either way, you can eliminate your hydrogen bromide here to produce your alkene, and another hydrogen bromide also, this part, to produce your alkyne. So sorry, alkene and then alkyne. Okay, and then you can think, how do you prepare this one? Okay, you can prepare, or how would this one can be prepared? And so you can think of your starting material. You can prepare this from here. You can have your addition reaction, HBr. So you can add your HBr from this. Then you can think like, what will be your starting material like that. Okay, so this is like a retrosynthetic analysis of how you can prepare your acetylene, phenylacetylene. So for this, now that's why you always have to compile with you all the kind of reactions that you have learned from chapters 8, 9, and 7, 6 point, no? 6, 7, you have the substitution reaction, you have the elimination reaction, and then you have the addition reaction. So 3 kinds of reactions. You have the substitution, okay, pag mo increase gani ang number of carbons, chain length, that must probably be substitution reactions, no? Where one of your nucleophiles na siya increased number of carbons. Okay, and then you can have your elimination reaction. So when your elimination reaction, you always produce your alkene or alkynes. And then you can have your addition reaction from your double or triple bond. Then you will have your halogenated products, or your mawala ang imong double or triple bond. That's for the addition. And then the other one is your radical reactions. No? So your radical reactions, usually you have your halogens in there. And if not halogens, you can have your katong pares kaganina, your NDS and bromosuccinimide. Okay, so for now, I would like you to not forget what you have learned in the previous chapters after midterm atong exam. You always have to remember them. And never forget on the mechanism, because when we do retrosynthetic analysis now of preparing of how we prepare our target compound, no, we always have to use the previous reactions and mechanisms. Okay, so NBS. Balikan na ninyo ni. So, balik na ko. So, for now today, we'll proceed. This is just an analysis reaction, and you'll have your NBS. Here again is your benzylic position, benzylic position, to produce this one. From here, you can actually produce this, not a benzylic position. So you will have to substitute this one, the benzylic position there. You can have here. So, pwede nimo, you have already planned your retrosynthetic pathway, then balihon na din ninyo. You can start with your starting material, for example, your phenylethane. Okay, you have here, and then you have your NBS, N-bromosuccinamide, 2 equivalents. And you can have substituted this, your bromine, to be added in here. Alternatively, you can also have your katong na learning you before, no, sa chapters 8, no, where you will use your sodium amide, no, where you eliminate this one. From here, no, you will eliminate this hydrogen and bromine to have this one. So alkene and then alkyne. So you have 2 eliminations reactions to produce this one. And then so this becomes your, of course, this is the problem earlier, that this will become your starting material. Your final product rather, and this your starting material. And so that is the alternately, you can have your NBS again, NBS, your N-bromosuccinamide, where you can substitute at the benzylic position with your bromine. And then once you have your bromine, you can do elimination reaction. You can eliminate hydrogen and bromine here. Katong, you have your hydroxide and heat, no? This is E2 elimination reaction. You can produce your alkene. Once you produce your alkene, you can also do addition reaction. You can have your bromine. Once you have your not vicinal, you have your vicinal dihalides. You can do substitution elimination reaction to produce your alkyne. I can review on that. You have already had this kind of example in the previous chapter. Sodium amide, no? And then we have the protonation, no, para dili siya alkynide, acetylenide or alkynide atong makuha. So we have protonation reaction here because this one is very basic. Otherwise, adiprotonate could always ang hydrogen here, because the hydrogen here from C triple bond H, or C SPH here, or SP carbon and hydrogen is very acidic. So that's why you need the protonation step here, which is H3O+ to have this one. So practice problem, show how the following compounds could be synthesized from phenylacetylene. So you have here 1-phenylpropyne, phenylbutane. So, okay, again, these are the application reactions of what you've learned before. And some, whenever you have the benzylic position, where you can substitute to have your kani. To have this substituted, no, whenever you have your alkyl halide, no, that will always then be the start of reaction. Okay, so for today, we'll be talking about the radical additions to alkenes, having the anti-Markovnikov addition of hydrogen bromide. We learned in chapters, I think 8, no, that when we do the addition reaction, you always have the Markovnikov addition. Okay, in this case, no, so before you have the orientation of the hydrogen bromide to alkenes is the subject of confusion. So we have before the Markovnikov's rule, and samantang Markovnikov's rule, you have the rich gets richer and the poor gets poorer kind of reaction. reaction. So here, so before we had that Markovnikov's addition, sa ganitong Markovnikov's addition, Shaira?
Yes, ma'am.
Ano sa ganitong Markovnikov's addition?
Katong the rich gets richer and the poor gets poorer, ma'am. Katong mo-add siya sa H ba to?
Yeah, the carbon that contains a higher number of hydrogen. That is where your hydrogen from your hydrogen halide will be added to, right? Tama ba, Shaira? Ano sa man to? For example, the next. For example, na kay C double bond C, no? And one of the carbon from the C double bond C na has a greater number of hydrogen, then that carbon containing a greater number of hydrogen, that is where the hydrogen will be added from HX. Nga naman yun. Okay, so whenever there is the presence of an organic peroxide, so an organic peroxide, you have your ROOR, or organic hydrogen peroxide, you have your OO. Mas magsumpay na ganin ng duha ka oxygen, na that is your peroxide. Okay, so when alkenes containing peroxides or hydroperoxides react with hydrogen bromide, what happens is that there is an anti-Markovnikov addition of the HBr, or your hydrogen halides. Okay, for example, now you have your double bond here, C double bond C, in the presence of HBr. Now your hydrogen halide, your hydrogen bromide, for example, from the Markovnikov's rule, the carbon here contains CH2. The body have two carbons, the other one contains only one. So you have your CH, so CH3, CH, double bond CH2. So you have your carbon bonded to carbon, and then two double bonds, and then one from the hydrogen. So it's bonded to 4 bonds. It has 4 bonds. There's only one hydrogen here, and there's two hydrogens here. From the Markovnikov's addition, now this carbon containing a higher number of hydrogen will have the hydrogen here added from your HBr, and the other carbon will carry with it the halogen. So that is the Markovnikov's rule. Okay, but in the presence of the peroxide, no, even if this carbon contains a higher number of hydrogen, what happens is it follows the anti-Markovnikov addition. So dili mo add si hydrogen, but instead si bromide. Dili mo add sa carbon containing a fewer number of hydrogens, that is where the hydrogen is being added here. So baliktad ang anti-Markovnikov's rule. Okay, so sa indicator na to, whenever there are peroxides present in the reactions, sa itong mga peroxide, katong na yung mga ROOR, or na kay ROOH. So magtapad na ganin ng duha ka oxygen that's already a peroxide or peroxy acids, no? Peroxide or hydroperoxide. Kana mga peroxy acids na hydroperoxide. Okay, so that is this one thing that you will note whenever you encounter such kind of reactions. So hydrogen fluoride, hydrogen chloride, and hydrogen iodide do not give anti-Markovnikov addition even when peroxides are present. So they don't. So the only hydrogen halide that will give the anti-Markovnikov addition is your, excuse me, hydrogen bromide. So walay effect ang peroxide's presence for your hydrogen fluoride, hydrogen chloride, and hydrogen iodide. So your HF, HCl, and your HI do not give anti-Markovnikov addition. Only for hydrogen bromide or HBr, it follows the radical chain reaction initiated by the peroxide. So let's look at the mechanism for that, no? So the first step, of course, whenever you have your peroxide, as with the previous example, no, the first is always the cleavage of this peroxide, kanang OO bond, no? Si oxygen bonded to another oxygen. These are the usual initiating reactant in any radical reactions. In most radical reactions, it's always the or mostly the peroxide. Of course, in the halogenation reactions, like you have your halogens, can have your halogens being the one that is being initiated in the presence of light, and UV can break that bonds, a ClCl for instance, or BrBr to form your halogen that for halogen radical, halide radicals. In this case, now whenever you have your OO, that's your peroxide, can have your radical here, so your OR radical. Once you have your OR radical, alkoxyl radical, no, it can do homolytic bond formation with your hydrogen halide, particularly only the HBr, hydrogen bromide, no, to form your ROH, your alcohol. And then you have your bromine radical, your halogen radical, Br dot. No? So one of the electrons, again, is not paired. So again, whenever you have an atom that has an unpaired electron, that is automatically become a radical. It's an unpaired, it contains an unpaired electron. So once you have your unpaired halogen here, then you will have your do the reactions with the double bond to form homolytic bond formation. Unsa nang homolytic bond formation? Again, the homolytic from the word homo, it only forms a bond with one electron from the other atom. So one electron comes from bromine and the other one electron to form a bond with carbon here comes from this. So asagikan from the pi bond. So you have your Br forming a bond with CH2 here. Okay, so you see one-sided arrow and one-sided arrow here coming here. It means that we only taking on using one electron from the bond. So one electron from bromine, you have one-sided arrow, and one electron from the pi bond here, one arrow. And since there is a homolytic bond cleavage in this carbon double bond carbon, one goes to the bond formation BrCH2, BrCH bond. The other goes to this carbon. So another arrow goes to this carbon with a dot. So what we get here is a 2-degree radical. Then you have your 2-degree radical. Now this is your radical. We have to have the